So what I want to do here is that I want to go back and finish our discussion on blackbody radiation and move on to the photoelectric effect. I think the blackbody radiation is one of the more subtle problems that classical physics faced. And I will do my very best to try to communicate that information to you. But without us really going into the mathematics, which I think is super cool, by the way, because you have to do some series expansions and you have to derive a probability distribution function. I'm going to try to avoid that because I really want to get to the physics, because this one's much harder to actually see. And so what I really want to focus on is that I want to focus on really the photoelectric effect and Compton scattering. Why? Because they're easier to see why it was an issue. Most people don't go over the blackbody radiation, but by going over the blackbody radiation, you're seeing why quantum mechanics had to exist. And I think that's a very powerful statement all by itself here. So I want to go in, review what we had last time, and then move forward from there. Okay, here we go. So what we were talking about last time is that we want to heat up a solid piece of metal, let's say. And that's what we typically think about. So I heat up a solid piece of metal. And what happens is that if I start off with the hot plate and I just warm it up just a little bit, what you end up finding here is that you end up getting into a situation where you actually sort of like, you can not see any light coming off of it, but what you're seeing is that you're seeing some type of, you're feeling infrared radiation. And then if I add more and more energy to this hot piece of metal, what is the light that's being radiated by this hot piece of metal? And what we find here is that in the end, we start to look at heating a piece of metal to heating a light bulb filament. And if you can continue on, what you're seeing here is that you're getting a shift in the intensity of the radiation. Not only as I go to higher and higher frequencies, it moves this way. By the way, this is not correct. There's no way that's the behavior. This is wavelength, not frequency. I actually prefer frequency, and I'm really struggling with writing wavelength because wavelength's not really the important thing. And so what I'm saying here is that you get this radiation curve. And the way I'll show it to you is that we can sort of like summarize this in this applet that I want to share with you. And this is a PhET applet, which they do a fantastic job. And what you're seeing here is that when you look at the temperature of the object, that curve that you get from heating up, let's say like a hot plate, is going to look something maybe not like that. It's actually going to be more further down. But if I increase the intensity, what you're seeing here is that look at the peak on this guy. The peak here, if this is 4, a scale of 4, and then this temperature looks like it's around 2300, 2400 K, that's still not a hot plate actually. So if you're looking at a hot plate, you got to bring this way down, like way down here, which you can't even see the curve. But if I start to increase this thing, you could see that this curve is way the heck out of here. So it's literally peaking in the infrared, and you're not seeing anything. But now I got to play this game of reducing the scales. Okay, and if I reduce the scales, as I start to heat these things up here in temperature, what you're finding is that the curve is moving from the infrared towards the visible. We're talking about the peak. And if I was to literally, so right now, when you're looking at the curve, you're seeing that this curve is in the, you're seeing part of the visible spectrum now. And as I continue to increase this thing, you're seeing that most of it is still in the infrared, but you're now getting a distribution of visible spectrum. Now, if I continue to increase, so look at the scale, this is 4 now on the intensity scale. So if I decrease this now and I increase the temperature, you could see here that as I'm getting hotter and hotter, the intensity is growing and there's a shift in the peak. It was in the infrared, now it's in the red here. And if I continue to do this and I keep decreasing this thing, look at the scale, it's 100. You could see that it's getting more and more intense. And so when you're reaching the temperatures of the sun here, this peak here is, I'm sure this is accurate, but I think this line is too thick. This peak should be more in this lime green, not in this, because so this is a little bit inaccurate.
You're just a little bit above the sun.
Oh, am I? Okay, I thought I was, because that should be around the sun right there. Oh, that scale for the sun is wrong. Because it's saying here, like when you get to the sun here,
So 8,500 K, is that right?
I think it's not 5,800. I think it's more like 5,300 if I remember correctly. So if I'm going below that, I think it's 5350. Well, maybe I'm wrong. But it peaks in the lime green section. Now, note that there's a range. So I think the scaling is actually not correct.
So I have a question about the intensity. What is the physical equivalent for the intensity buttons? I notice as you increase the temperature, the intensity does seem to track with it, but it also changes.
No, but this scale, you fix it. So the problem is that if I increase the intensity, you can see I'm over 100. So then I reduce it, and then you get a higher intensity scale.
Okay, so but like with a hot plate, how do you increase the intensity of the profile that you have without increasing the temperature of the hot plate?
You can't. That's the point, is that if I start to heat this thing up, the intensity literally is going to get higher automatically.
So there's no physical equivalent to the plus minus buttons you have there?
No, nothing. No equivalent. And so, but I think it's worth really looking at this thing. And even though this is not a beautiful curve, I think one of the things that we should probably do here is that we should capture this. Actually, this isn't black. I don't know if I want that in black. And I think the really important thing here to look at is something like this here. And I'm gonna snag a different image of the radiation curve, just so that I can share this with the screen with you, so you could get a better sense of what I'm trying to actually point out to you right here. So I'm assuming that you're seeing my screen right now. Yep. And one of the things that you want to pay attention to here, oh, come on, there we go, is that here's the radiation curve. And you could see how the temperatures are changing. But what I want you to really look at is this. So if you analyze this curve, what you're seeing here is that you're seeing this type of thing. Note that when I look in this region here, and then I want you to look at the other region here. Let's say I pick this guy here. One of the things that I want you to realize, note that there are many, or much more, there's, how do I say this? Many more low frequency spectrum, right? The tail is really long, but when you look at this lime green section, there's very few high frequency spectra. And that becomes really important in the discussion. So when you're looking at this thing here, you're getting a lot more low frequencies and you're getting not nearly as many high frequencies from the peak, that is. And so now let's kind of summarize what actually happens then. Okay, so that's what we're seeing in the applet. But now what I want to do here is that I want to essentially review what we talked about this time. But this time I want to talk about an oven. And when you bake something in your oven, a very common temperature is what? 400 degrees Fahrenheit. So let's go look at that thing here. So now I want you to do the following thing. I want you to imagine okay, you set your oven to 400 degrees Fahrenheit. And what you do here is that, of course, you give it time to warm up here. So when you set your oven to 400 degrees Fahrenheit, you are heating the walls of the oven. And as you heat the walls of the oven, you generate electromagnetic waves of what we call radiation. Okay, so in other words, when I'm thinking about my oven, I imagine that I have walls here. So I heat up my oven, and of course, my oven right here, we're going to call the inside of this thing, right? Inside of here, of course, is the cavity of the oven, and then these are the walls. So as the walls heat up, they're emitting electromagnetic radiation into the interior. So in other words, these walls are emitting, right, radiation into the cavity. So it is this radiation that is called black body radiation. Okay, that's the black body radiation. And this radiation, where this radiation is from hot objects. So if you heat up a hot poker, if you look at the sun, if you look at a toaster oven or, you know, an electric heater, and what you're finding here is that this is what this black body radiation curve looks like. Okay, so when I'm looking at this black body radiation curve, what we're actually seeing here is that you could imagine that you do this thing here. Here's my intensity. And I really hate doing this, but a lot of the people are actually doing this in terms of wavelength. It should be in frequency, but I'm going to do it in wavelength because I think the applet is in wavelength. A lot of the images in the textbook are in wavelength. And so what you find here, so if you heat up an object, it's going to produce a curve that looks something like this. And I'm going to say that this object right here is a cooler object, sort of like the hot plate. And so what happens next is that if you can continue to heat this thing, okay? If you can continue to heat this thing, what happens here is that the peak shifts to the left. So this orange line here tells you that it's getting hotter, but the intensity is growing higher. And then if you continue to heat this thing shifts even more here. And what you're finding here is that this object is a hotter object, and the hotter object not only has a shift in the wavelength of light, right? So if I'm looking at the peaks here, if I compare the red peak, let's say, for example, you heat up an oven, right? You heat up an oven and you're able to heat this guy up to, let's say that the red here has a temperature of 500 degrees C. What is 500 degrees C? We say that the light emitted by a cooler object, right, emits longer waves or lower frequencies. But if I look at this yellow one now, this yellow one I would say is at a higher temperature. Let's say that this curve here, this makes me a little bit nervous writing in yellow. Can you guys see this yellow? Okay, so when I look at this yellow here, this is, let's say this is 1,000 degrees C. So then this guy tells me that it's the light emitted is, light emitted by hotter object, then tells me that it does what? It does shorter wavelengths or shorter waves, and it has higher frequency. So the black body radiation tells me that not only is it brighter, but I'm getting shorter waves.
Another feature of this drawing that you've built in here is that the waves of lower frequency are still the same intensity. Is that accurate?
No.
In a hotter object,
the intensity is higher, which is what I was just going to write right now. So in summary, we see that the intensities of hotter objects is much higher than cooler objects. And if we were in lecture and I could just demo this, you'd go like, well, yeah, of course. But it's hard, so that how we can't have that. But then what you're seeing here is that hotter objects emit light of shorter waves. Now, I should be careful when I say that. I really mean that the peak is at a shorter wavelength, right? So hotter objects emit a spectrum of more shorter waves while cooler objects emit more longer waves. And in fact, there's a law that actually talks about this. It's called Wien's law. And Wien's law is essentially telling you exactly what you're seeing right here. So the key thing here is that note that the peak of the intensity curve moves towards the lower frequency region. So that means we're moving in shorter waves this way. So if I increase the intensity, the peak of the wave is going to the left. Now, in 1900, the shortest waves that they knew about was ultraviolet. So in 1900, the shortest known waves were ultraviolet, UV light. Okay, that was the shortest waves at that time.
Hey, Carlos,
Yeah,
when you said peak of the intensity curve moves towards lower frequency region, if it's moving to the left, is
no,
that
no. Did I say lower frequencies? Oh,
lower
it should say
frequency
higher. It
region?
should say higher. Thank you.
Okay.
It should say higher. Thank you for the correction. Yeah, I'm thinking frequency and trying to translate into wavelength. Physics at the upper levels do it in frequency. At this level, everybody does it in wavelength, which is driving me nuts. But I'll handle it. So the question is this here. Okay, so the question is this. What does classical physics have to say about this? In other words, if you were to calculate the intensity curve for a hot piece of metal, what does classical physics tell you here? Well, what it does here is it does the following thing. So if you look at the answer to this thing here, classical physics calculates that the total energy inside the oven set at 400 degrees Fahrenheit is infinite. Let me say this one more time. That if you turn on your oven to 400 degrees Fahrenheit, your oven will produce an infinite amount of radiation. Now, just think about if you had an infinite amount of radiation. Could you imagine your PG&E bill? PG&E just needs you to turn on the oven one time, then you owe them an infinite amount of money. But at the same time, if you had an oven that produced an infinite amount of energy, that means it's producing an infinite amount of radiation, which would kill every living thing in the universe. So classical physics is clearly wrong, and there's a problem. And so what do I mean by that? What I mean by is that, let's go back to the picture-wise. So picture-wise, this infinite amount of energy is called the ultraviolet, the UV catastrophe. Okay, so when you're looking at this catastrophe here, which it would be, right? Because a catastrophe would clearly take out all living things on Earth here. This is what they mean. And so picture-wise, it kind of looks like this here. So here's my intensity again. And then I'm going to look at my curve. So if I look at my curve kind of looks like this, and then it goes like that. So this is the radiation curve. This is the Blackbody radiation curve. And when I look at classical physics, what does classical physics actually predict? Well, it predicts that the best that classical physics can actually do, it does this. So this curve here, this is the best prediction by classical physics. And this is known as the Rayleigh-Jeans law. And you could see that, and what you're seeing, there's a couple things here. It predicts very well the low energy or long wavelength spectrum. So it does really good down here. So it does really good. But it fails miserably here. So the question is, why? And so there's the infinite energy right here. So if you look at this, this is the infinite energy right here. And so the reason why they call it the ultraviolet catastrophe is that at that time, that was the shortest wavelengths that they knew about. And since it was the shortest wavelengths that they knew about it, they just says as you go towards the ultraviolet, you get infinite amount of energy here. So I said that there was Wien's law. When you look at this Wien's law right here, Wien's law turns out that it actually predicted the other side of the spectrum pretty well. And this is Wien's law. But Wien's law had a lot of issues. So they knew that that wasn't the best classical answer to the Blackbody radiation curve. And Wien's law is also an experimental thing, not a theoretical calculation. It was really an experimental observation more than anything else. So the question is that we want to understand this problem and how it got resolved. So how do we solve this infinite radiation problem? And the way we do that, so it's important to understand how this problem was resolved by none other than Planck. And when you do this, this is the first major problem with classical physics. And in essence, this is the birth of quantum mechanics right here. And even though we have a long ways to go to really explain what quantum mechanics is, but this was the first sort of crack in what actually happens here. So what are we talking about here now? So now what I need to do here is I need to get you a picture so that you could imagine what's happening here. So what we do here is that we focus on the atoms in the walls of the oven. Okay, so when you focus on the walls of the oven, what you're actually imagining here is that you can imagine that we have an oven with a cavity. And so what you're seeing here is that these are the walls. And what you're finding is that inside the oven walls are little atoms. So these little guys here, here's are the atoms. And when you heat up the walls of the oven, what starts to happen? You oscillate these atoms. So when you focus on that, what you're finding here is that when walls are heated, atoms begin oscillating. And remember what we said about this thing before, that if you have an oscillating charge, then what ends up happening is that it emits electromagnetic radiation. So you could imagine that I have these atoms where I'm oscillating them, and they emit electromagnetic radiation. But now, though, is that you got to think about the heating. If I heat things to low temperatures, those atoms have low energy. But if I heat them to high temperatures, they have higher energies. And so what we're saying here is that the radiation is dependent on the temperature of the walls. Okay? And so what happens then is that I'm getting this radiation that's literally coming in, and it's sort of like this radiation is sort of like filling this whole cavity as it's going there. Now note, there's atoms everywhere, right? There's atoms all over the thing. Even though I just drew them on one side, they're everywhere in the walls of this container, of the walls of this thing here, right? So these atoms, they're oscillating in the walls of the oven here. Now, here we go. So what do we know about Maxwell's equations? And the first thing that I should do here is that I want to give you an analogy. And this is from Physics 4a. Now, you may remember standing waves in Physics 4a. So if you look at standing waves, what you do here is that you have two ends that are fixed. Okay? This and this here, these are fixed ends. And then what you do here is that you come in and you put an oscillator on a string. So you could imagine that this right here is a string right here. An elastic string. So what happens? If you oscillate this thing just right, what you're going to get here is that you're going to get a standing wave problem where the wave will oscillate back and forth between these two fixed points. And so if I do this again, what you'll find here is that as I increase the frequency of this thing, I shorten the waves. But as I increase it, what you're seeing here is that you can get a pattern that looks like, let's say, it can look something like this, and then the wave reflects. And I know that this isn't symmetric. If it really bothers you, squint, it might help. And then if you look at the next higher frequency, you might get a pattern that looks like this here. So what you're seeing here is that you're getting wave modes. So in this case, this is typically called the fundamental or the first harmonic. And then you get the second, and then you get the third, and then I can just keep going on and on and on and on. And what you find here is that what describes these standing waves here is it's called the resonant frequency condition. So if I have the resonant frequency condition, it says this, that the frequency of all of the standing wave modes is equal to n times f1. So what you really got to do here is that you actually have to solve a second order differential equation. And when you solve the second order differential equation, what ends up here is that this frequency condition pops out, because it's the only way that you can meet the boundary conditions at, let's say, x equal to 0 and x equal to L. This is what actually pops out right here. And it's not really important that we derive it, but you can. It's a fairly straightforward thing to derive here. And the other condition that we find here is that we find that all waves have the same speed. But wait a minute, if they have the same speed, then that means that the speed is always a constant, but that tells me that associated with that is the wavelength and the frequency. So that means if I have long waves, I must have a low frequency. If I have a short waves, I must have a high frequency. And everything is dictated by this resonant frequency condition here. So now that I've kind of reviewed this thing, guess what? When I look at my box, my oven, so now back to Maxwell's equation. The oven sets up a three-dimensional standing waves in the oven. Very similar to the strings right there. And what you're finding here is that, so if I now go and I look at this thing here, what Maxwell's equations tell us then, so Maxwell's equations imply that electromagnetic waves generate within the oven standing waves. And you may have actually even seen this, right? Because you could put in a layer of marshmallows into an oven and you can actually see a standing wave pattern where it melts part of the marshmallow in some places and not in other places here.
Is it a microwave that you're talking about?
Sure. I mean, just saying that you get standing waves produced in a microwave, but then if you have one of these microwave stirrers, then it actually tries it. You don't get the pattern so nicely.
You get
But
a
if you
revolve
take the
pattern.
but if you take the stirrer out, you'll get standing wave patterns. In fact, they even talk about measuring the speed of light in a microwave by melting a sheet of chocolate. I mean, I mean, that seems like that's a good way to waste chocolate, but yeah. Moving on here. So what this really means here, but let's be really careful. Standing waves generated within the oven form standing waves. So what does that mean though? What that means here is that only a whole number of waves can fit perfectly between the two walls of the oven. Right? Only two. And so what you're doing here is that I'm going to use this word very, very carefully. This reduces the number of available wave modes. If you don't have a whole number of waves, or half waves, let me be careful, then you can't produce, those will never occur. So this thing here, it acts as a suppression factor. Okay, it acts, and that's an important piece because that's exactly what Maxwell has done. So now let's go to the next piece here. So now that what we want to ask here, we want to ask another question here. The question is, and I think I asked this up here, didn't I? No, I think the question is, what does classical physics have to say about this? So I'm still answering the same question. What is the problem with classical physics? And the answer to this thing here is that classical physics is able to determine how much energy a oven's hot walls will pump into the cavity. So classical physics calculates how much electromagnetic wave energy is pumped into the oven. Okay, they can calculate how much energy is pumped into the oven. Now, what happens here is that here's the main problem right here. Okay, and the main problem is this, is that from physics 4C, there is the equipartition theorem. And remember what the equipartition theorem says. It says that it must divide the degrees of freedom evenly to all degrees of freedom, right? It must divide all the degrees of freedom equally. And in this case, equally to all wave modes. It must divide the energy equally between all wave modes, regardless of the wavelength. But wait a minute, that's a problem, right? That's a problem. And one of the things that I really came back and I tried to show you here is that let's go look at this thing again. So here's again my intensity, my blackbody radiation curve. And so if I go and I redraw this thing, that doesn't look like that's symmetric there, right? So if I'm looking at this guy here, this is not symmetric. So what you're looking at this thing here is that look what's happening over here. Over here, you're getting a lot more low frequency region. And then over here, if you look at these guys right here, right, look at these guys right here, what you're seeing that, as I'm saying here, that there's a lot more long wavelengths than short ones. So you could see that there's a problem when you go and just look at the radiation curve. There's a problem with that. But nonetheless, that's really the downfall of classical physics right there. And if you had really looked at this thing, it would have been able to tell you this. So look at that. So regardless of the wavelength. So what that says here, so if I look at the equipartition theorem, it then says that all possible waves, or wave patterns, I should say, not waves, within the oven are on completely equal footing. When it comes for atomic oscillators to emit radiation into the cavity. This is the cause of the ultraviolet catastrophe right here. It is the cause of the ultraviolet catastrophe because even though you're looking at this thing experimentally, you could see that there's a lot more green than red. So how could they be symmetrically, given that way? So what you find here, so here's the downfall now. Even though I've said it, let's spell it out. The downfall of classical physics. So when I look at the downfall of classical physics, we could just list them up. Here we go. There are an infinite number of possible standing waves. Right? There's an infinite number of possible standing waves within the walls. And so what that means here, that when I look at my resonant frequency condition, you could see that n, since it has to be whole numbers, goes all the way to infinity. So I have an infinite number of modes. So then the partition theorem, or the equipartition theorem, says each mode, carries the same amount of energy. So you have to equally divide the degrees of freedom between every single mode. And so clearly, if you have equal amounts of energy for each of these modes, then this tells you then that this translates then as an infinite amount of blackbody radiation. And that's where classical physics fails. Because when you turn on your oven, you don't have an infinite electric bill or kill every living thing in the world. So clearly classical physics has failed here. So then we go into the details now. So now along comes Planck's. So this is Planck's solution to the infinite energy problem. But what does everybody else call it? The ultraviolet catastrophe. But I think the ultraviolet catastrophe doesn't really tell you that it's an infinite energy problem. So I like to call it the infinite energy problem. Now, so what did Planck do? The first thing you got to realize is that Planck is a first-rate mathematician. He's really good at math. And so he starts out by parameterizing the blackbody radiation curve. Okay. And what he does here is that here's the crazy thing. Planck realizes that there are two, how do I call them? Half-laws that describe the radiation curve. And this is something that I showed you earlier, that when he looks at the curve, he says, well, let's look at this curve, right? So you have a curve that looks like this. And so when he looks at this curve, what he's actually saying here is he says, well, there's the Jeans law. The Rayleigh genes does really, 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 really good at low frequencies. So the Rayleigh genes law does really good. And even though they knew Wien's law didn't work very good, they knew that it actually did really good at short wavelengths. So like any good mathematician, he says, the very first thing that you got to do is you got to parameterize the curve. So essentially adds, okay, he almost adds these two together, but it gives him a good head start on how to write down the equation that parameterizes this curve. So Planck using straight up mathematics writes down the exact equation that parameterizes this curve. Okay? So he gets this mathematical equation. He doesn't use any physics at all. He just uses pure mathematics. And so now he says, so in other words, there was no physical basis for this equation. None whatsoever. But like any good physics person, he then tries to describe physically what is going on. So now Planck then tries to interpret the mathematics into physics. And he came up with two really bold statements. I mean, you know, Planck is sometimes called the reluctant revolutionist in terms of physics terms. He did not want to revolutionize physics. He liked physics the way it was. And so here's what he did here. So then he boldly guesses two important points. Okay, the first one is now known as energy is quantized. And I'll be honest, this one really bothers me. This is one of those things that I really don't like to think about it that much. And it essentially says that, he says this here, that the energy emitted by the atomic oscillators and the walls of the oven come in little discrete lumps. So his thing here is, it says that the energy emitted by the atomic oscillators come in little, as he says it, little discrete lumps. Okay? But even though he says that, look what he says next. What he says that, what he really means by this statement is that atomic oscillators can only emit or absorb energy or energies in lumps of a certain size. And what he does here is he says that these guys have a minimum energy, which I'll just call E min. And that this minimum energy is what they call the quantized energy. So just imagine that you have an oscillator. This is kind of a crazy thing. Like one of the things that I asked my Physics 4A students to do is that they have to write a modeling project for an oscillator. And so you could imagine that we have a mass on a spring. And let's say that this is the oscillation here. And then I pull down this mass. So as this mass is going down, right, that means that the spring has now stretched out and then it comes back up, maybe not that high up, but you know, what you're finding here is that this thing's then going to oscillate. So if when you look at this oscillation, the oscillation then goes something like this here. So my students actually end up modeling this thing here, but there's really two things that are really going on. This oscillator here is losing energy. And if you were to actually do the mathematics, you find that the spring is heating up and cooling off, heating up and cooling off. So what you find here is that there's this sort of like exponential decay that goes on. So if you actually look at this thing, I have a little oscillator, and what's this oscillator really doing? Well, it's actually doing this type of thing. Right? It's losing energy as a result of this thing. Right? We can imagine how this thing loses energy. But now, if you look at this picture, so now under Planck, what am I actually seeing here? I have an oscillator, right? Let's say this is my little oscillator and it's oscillating. So as this guy oscillates up and down, this oscillator also loses energy. But how does it lose energy? It's throwing something off. You're getting these energy packets or energy lumps that somehow get thrown off like this. Here, you see this smooth transition as the oscillator's losing energy. Here, right, this being my atomic oscillator, there's nothing smooth about this. You're getting this discrete minimums, and each of these carries a minimum amount of energy. Now, I don't know how you imagine this, but that's exactly what he's saying here. So he's saying that all oscillators have this minimum amount of energy that they can emit, right? So this guy tells us that this is the minimum that can be emitted. So that means, I mean, if I was to give you just a brief analogy of how strange this is, I mean, it's not so strange when you think about that. Think about money. I mean, what's the denomination of all American money? It's got to be the 1 cent piece, right? You could have, you know, 100 million pennies. You could have 10 pennies, right? That's possible. But one can never have like 0.36 cents.
I mean, not
right?
really true, but in hand, I suppose.
Yeah. I mean, what do you mean? You like cut the penny up and take that to the store and say, I want to buy this for 0.36 cents?
Yeah, I mean, I don't know how useful the analogy is in the like stock trades, like fractions of a penny. That side note.
Okay, I'm thinking, okay, what about eggs? Let's say you want to go borrow eggs. Hey, Jason, can I borrow a third of an egg?
You can try.
Yeah, yeah, that's, you know, George Gamow. God, that guy's so funny. He's one of my favorites. He says, yeah, this quantization of Planck, he says it's like a pint of beer. You can't take a swallow of a beer. You can't drink half a beer. You can only drink denominations of 1 pint. So you go, that's it. if you want to take another beer, you got to drink a whole pint. He says, that's great because then I'm done after a minute or two. Because you just, I mean, so he has so many great analogies. So that is really, really out there. So if I was to try to summarize this thing, so that means here that each tiny oscillator has what? It has a minimum energy. This minimum energy is what he calls E-min, that can be emitted into the oven. The other thing that he says here that you can that they can emit, that each tiny oscillator can emit multiples of E-min. That means that I could have an energy En where N is in E-min, like this here, where N here is this quantized number that is only a whole integer. Now, if you're experienced with differential equations, you could see that when you look at the boundary conditions typically have these types of conditions. These allowed energies are said to be quantized. But here's the strange thing about this. There is no zero energy value. That means N equal to 0 is not a possibility. And by the way, if you've ever taken chemistry and you've talked about atoms and they talk about the ground state energy, guess what? This is the origin of it right here. It was Planck that essentially discovered that issue. And then he says something really interesting. This brings us to our second case. Energy is proportional. It's not the way we spell proportional. I should have just put quotes on the damn thing. It's proportional to frequency. And he was the first guy to actually write this down. And what he says here, he says that E-min is proportional to frequency. And he got this from parameterizing the radiation curve. It fell out of the radiation curve. And so then he goes, okay, so here's the min, and then here's the frequency. And for the first time ever, from the radiation curve, he defines the proportionality constant. And this is one of the most important proportionality constants in all of the history of physics, where H is now known as Planck's constant. And this is the one that I said is about 10 to the negative 34 joules seconds. Not good units, but nonetheless, it's there. And so what the hell does he mean when he says this? He means this here. He says that if you have a higher energy, higher frequency, then this means that the tiny oscillator has to emit a higher energy, minimum energy, or higher, damn it, a higher minimum energy. Or if you have a lower frequency, then this little tiny oscillator has to emit a lower minimum energy. You know, I keep saying emit, but it also has to absorb the same amount. So if I was to draw a picture, so if I look at visible light, right, violet, right, if we look at violet light versus red light, we know that violet light here has a what? This means that it has higher frequency. And then red here means that it has a lower frequency. So when I look at atoms, okay, so if I have a higher frequency atom, let's say that this guy I'll color in violet here, that means when this thing oscillates, when it emits a lump of energy, this little lump of energy right here must be at a higher minimum energy. Note, I didn't draw a wave. There is no wave. All of a sudden, this sucker is coming right out. And then if I have a red atom, if I could say that, what does it do? It emits a lump. But this lump has a much smaller minimum energy. Again, right? This thing comes shooting out. And there's some really strange shit that's going on right here. Really, really strange shit. And so the question is this here. Let me see if I could get you to understand here. So when I look at my oven again, so you could imagine here's the oven here. And then I have my oscillators. And here's something that I've always found to be really strange. Okay, so here's my little red oscillator and it's going up and down. And this has always been a kicker for me. But check this out. Here's what Planck says. He says, this little SOB that just got knocked out of here, right? This guy's being thrown into here. So all of a sudden, the walls here, it starts out lumpy, but becomes a wave, but becomes a smooth electromagnetic wave in the oven cavity. So you got to ask yourself, if you throw in a lumpy thing into a cavity, how does it become smooth? Well, I mean, I really kind of struggled with this thing, but another analogy that you could do here, what happens if you have drops of water that fall into a pool? As you drop more and more and more water drops, it becomes what? You can get ocean, you can get waves that are in this pool now. And that's what he was imagining. Well, it's Einstein that's going to shock him and saying like that, no, dude, that's not the way it works. So he did, but that's kind of what he's thinking right here. And if I have a violet one, oops, That's not what I'm looking at. So now if I go and I look at my violet wave, and this guy's oscillating here, it also throws out this little packet of energy, right? And as it throws this little packet of energy into that, you're getting what? You're getting a spectrum. So I could emit green, right? And what's that spectrum look like? Oh man, I don't want to put that spectrum out. But I mean, I guess I could come in here and I'll just show you what I mean, but then I'll move, I'm going to delete it right away. But just to remind you, let me see if I can get this thing to go. So look at the spectrum here. So if I look at the spectrum, this lumpiness tells me that if I look at this one curve here, then that means that all of this region right in here, that's going to be the infrared lumps that are being emitted. And then you can see there's a little bit of red, there's a little bit more yellow. You're emitting them, but you're emitting mostly the other ones. And if you're looking over here, you're getting other lumps here. You're getting UV, you're getting X-rays, you're getting gamma rays, right? You're getting all these other lumps too. So he's saying that in the walls of your oven, you do emit X-rays. You do emit lumps of gamma rays too, which is kind of surprising when you think about that. But he's saying there is. But the hint in this whole thing is, remember what I said. Look at the curve. There's a suppression that goes on. You could see that in this region right here, there's less, but in this region over here, there's more. So there's a suppression that's going on, and that's where Planck is actually getting here. So now, here's the punchline. On how Planck solves the infinite energy problem. In other words, the ultraviolet catastrophe. Here's the punchline. So what he says here is he says the following thing. He says, he looks at the curve, just like I've been trying to tell you here, and he says the very high frequency oscillations are the ones that contribute the infinite amount of energy. In other words, the very high frequency oscillations are the ones that contribute an infinite amount of energy, right? They contribute. And look at what classical physics does. What does classical physics says? Look at the curve. This is the classical physics line right here. And you could see there is my infinite energy right there. So it's these little SOBs and the lime green that are causing the infinite energy here. So the goal here is that he says here that these oscillation modes must be suppressed. To rectify, how do you spell rectify? Something like this. And I think I got to stop here. But that's where he now goes in and he rectifies the problem by saying there's a way to suppress these things. And he derives it. He derives it in this beautiful, discrete summation that goes off to infinity. And you get this really sexy equation.